describe supersonic speed and shock waves. These are the key concepts that we will dwell on: wave fronts, Huygens principle, diffraction, interference, shock waves, also the concept of the Mach number. Let's begin by looking at wave fronts. But before we continue, let's just do a quick recall from grade 10 or 11 work. Remember that a wave is an oscillation or a disturbance in space that transfers energy from one point to another. Here is an example: a stone that is thrown into a pond. You get circular waves like that one. The stone is thrown into the center and then it generates circular waves as shown in this diagram. Another example is an example of straight waves that look like that. In this case, the vibrating object would be here, thereby creating waves that move in this direction and look like that. We call them straight waves. A wave front is an imaginary line connecting adjacent points on a wave that are in phase. These points are in phase. Example would be crests or troughs of a wave cycle. And here we have a diagram showing wave fronts. Here we have got circular waves. Here we've got straight waves. The lines basically that we've got here indicate the direction of the movement of the wave. So in this case, the wave is moving outward in circular format, and there the wave is moving in that direction. And the lines, these solid lines, the red lines, are representing the actual wave fronts. And in a wave, we know we've got crests and troughs. So in this example here, the lines will be the crest, the highest point on a wave, and the spaces in between are the troughs. Similarly, on your straight waves here, the lines represent the crests and the spaces in between represent the troughs. A principle that helps us understand wave behavior is called Huygens principle. This principle states that every point on a wavefront acts as the source of secondary wavelets that spread out in all directions with the same speed as the wave. And how you find the wavefront is basically that the new wavefront that is found, it is found by constructing the surface tangent to the secondary wavelets. For example, here we've got a single point, and this line therefore would be your first wavefront, and from that wavefront comes the secondary wavelet. Now, if you've got more than one point, you've got a series of points as shown over there, and there you see your secondary wavelets, and then you draw a tangent to these waves, and so that would be your second wavefront over there. And so you can continue like that. There's your first wavefront, and the wavelets that spread out from that wavefront. Then you draw a tangent, second wavefront, and the wavelets that spread out from that, and there you have your third wavefront, and you can continue like that. There's an interesting phenomenon that is observed when you take water waves that are generated by a ripple tank and allow them to pass through an opening. And that phenomenon is called diffraction. By definition, diffraction is the bending of waves around the edges of an obstacle or an opening. Here we've got a diagram, a simple diagram, looking at straight waves, and as they go past that barrier, they bend around the edges of that barrier. That is an example of a diffraction pattern. And let's explain diffraction using Huygens principle. Now, according to Huygens principle, we would remember that the wavefronts create wavelets. So as the wavefront goes through the opening, let's have our diagram over there. There you have our points, and there's your first wavefront, and there you have your secondary wavelets that are produced there. So according to Huygens principle, as the wavefront goes through the opening, every point gives rise to the secondary wavelets. And these wavelets spread out in all directions, and again we've explained this before, and this also includes the area behind the edges of the opening, and this is why we then have the diffraction pattern that is often observed. Please note that the speed of the waves as they go through the opening does not change. In other words, the speed of the waves does not change when the wave diffracts. There are various degrees of diffraction. In fact, the degree of diffraction is greatest when the gap is smaller or comparable to the wavelength of the waves. We'll explain this using diagrams, starting with this situation where the gap, here's the gap, is larger than the wavelength of the waves. Here we have some diffraction, but it's really a small amount of diffraction, a small degree of diffraction. What happens when the gap width is approximately the same as the wavelength or even less than the wavelength of those particular waves? Well, this is what we observe. Let's use a line diagram to explain it clearly. Clearly you can see there that we actually have more diffraction, a large degree of diffraction. In other words, we can conclude from these two diagrams that diffraction increases as the gap width decreases. Also, waves with longer wavelengths diffract more than waves of shorter wavelength through the same gap. As a quick challenge for you, a water wave has a wavelength of 3 centimeters. In one tank, it passes through a 2 centimeter gap, and in another tank, it passes through a gap of 5 centimeters. Which situation will show greater diffraction and why? This is a simple question, isn't it? Well, here's the answer. The wave will diffract more through the 2 centimeter gap because the width of the gap is smaller than the wavelength of the actual wave. What about diffraction of light and sound waves? Let's do a quick comparison, starting with sound waves. Sound waves are known to have long wavelengths. These can be measured in centimeters, sometimes even in meters. And because of that, they diffract very well through doors and windows of comparable sizes. This means that humans can hear around the corners of doorways, etc. In fact, you can even hear someone outside a room. Light waves. They have got very small wavelengths. These vary between 400 nanometers to 800 nanometers for visible light. And because of that, their wavelengths are way too small to diffract through doors and windows. In fact, the width of the door or the window is much, much bigger than the actual wavelengths of light. And so humans cannot see around corners. We can't see around corners. Light waves, in fact, will only diffract well when the slit or when the gap width is very, very small. We're talking micrometers or nanometers. Now, we said that light will diffract when the slit is very small. Well, let's have a look at single slit diffraction of light. And here's a simple diagram illustrating what we want to discuss. Over here, we've got a light source. And there we have a single slit. The slit is very small. And that's the diffraction pattern that you would see. Now, the type of light that we normally use monochromatic light. In other words, the same frequency type of light. Or if we use red light, we use red light or blue light. That's what we mean by monochromatic light, single frequency. And normally, the slit width is very, very small, approximately 600 nanometers, which is similar to the wavelength of light. So what we see is that the screen shows a broad central band, and there we have a broad central band. This then flanked by darker lines. We refer to these lines as fringes, and then other narrow light bands. So we've got a broad central band flanked by these dark fringes, and then we've got a series of lighter light bands or narrower light bands. Here is an example of a diffraction pattern that would be observed when we have blue light, and here is an example of a diffraction pattern that would be observed when we have red light. In fact, on this one, we've even shown you the light intensity. In other words, when we have our central band, there the light intensity is much stronger. Now, here's a question for you. I'm sure you can see this, that the diffraction of red light shows a broader central band than the blue light. There's the diffraction pattern in red light. We see clearly a much broader central band than on this one. There's the diffraction pattern of blue light, and we've got a central band which is not as broad as that one of the red light. Why do you think that is the case? Well, let me help you. It's actually very simple. You'll remember when we looked at the visible spectrum, we said that red light has got a longer wavelength than blue light. We also said that the longer the wavelength, the higher the degree of diffraction, and that is why red light shows a broader central band than blue light. An explanation for the single slit diffraction patterns that we observe. Basically, when the light is passed through the single slit, diffraction takes place and the wavelets, according to Huygens' principle, start to interfere with one another. Constructive interference of the wavelets results in the bright bands, and destructive interference of the wavelets results in the fringes. We'll talk about interference at a later stage, but it should not be a strange concept to you. And so that is what you would see. So the light bands are the results of constructive interference, and the dark bands are the results of destructive interference. The position of the dark fringes can be explained as follows. And here we have a diagram on which we follow the path of a particular light beam of wavelength lambda as it goes through the slit, and there we see a diffraction pattern. And we have a point P, which is the point at the center of the central band, and we have the point Q, which is basically the distance from point P to our first dark fringe, and theta is the symbol that we use for the position of the dark fringes. And so the position of the dark fringes can be calculated using this formula. Sine theta equals to lambda m divided by A, where A is the width of the slit, and of course lambda stands for the wavelength of that particular light, and m is the order of the fringes from the center. From the center, in this case, from point P, and m is cannot be 0, so it can either be plus or minus. For example, we have m minus 1 above the central point and m plus 1 on this side. And we can continue like that, m plus 2 and m minus 2. And of course, we said that theta is the direction of the fringe. For example, we can have a position of a second order fringe in the negative direction, and when we do calculate using the formula sine theta, and this is what it would look like. Sine theta equals to minus 2 lambda divided by A, negative because the fringe that we are talking about is on the negative side. Also, it is the second order fringe. That's why we then have 2 over there. Challenge number 2. Find the position of the first dark band formed on the screen when red light of wavelength 650 nanometers passes through a slit of 6.0 micrometers, and compare this with the position of the first dark band when blue light of 480 nanometers is used. Let's have a look at the solution. Start with the red light. That's what we are given. We're looking for the first dark band, so m is equal to 1. The wavelength is given 650 nanometers. Remember, nano is times 10 to the minus 9, and the width of the slit is 6 times 10 to the minus 6. 10 to the minus 6 is micro, and so we substitute in the formula. Sine theta equals to m lambda divided by A, and so we have we're looking for the first dark band, and there's our wavelength, and there's our slit width. And so the answer is that the first dark band would be found at an angle 6.22 degrees from the center of the central band. Look at blue light. We know the wavelength is 480 nanometers, and again we substitute, and the final answer is that in blue light the first dark band would be found at that angle, which is slightly smaller than that of red light. and that means that red light is diffracted more than blue light, as we've been saying. We used the concept of interference to explain some of the diffraction patterns that we have observed. Let's quickly revise in case you have forgotten what interference is. Interference occurs when pulses or waves overlap, and if you consider two identical waves of the same wavelength and same amplitude moving in opposite directions like this, according to the superposition principle, the amplitude of the combined waves is the numerical sum of the individual heights of the original waves. And so in constructive interference, the wave fronts are in phase. In other words, crests meet crests and troughs meet troughs, as shown over here. And if you have a look at the diagram, those are the wave fronts. In this case, the one-dimensional wave fronts of crests and the one-dimensional wave fronts of the troughs. And when these two meet, when crest meets crests and troughs meet troughs, the resultant is that the amplitude is much larger, and so that's the resultant wave that you would observe. In destructive interference, the wave fronts are out of phase. In other words, crests meet troughs, as shown over here in this diagram. Again, there you have your 1D wave fronts of the crests and the troughs. The resultant in this case is an amplitude of 0. In other words, the medium, if you were to observe in the case of water waves, the medium appears still, not to be moving. And in terms of our diagram, you'll simply represent it by a line like this one. When two identical waves continually travel back and forth, a standing wave is formed. And this is what a standing wave looks like. In a standing wave, you have what we call nodes. These points here are called nodes. And you have what we call antinodes. And it is these highest points here that are called antinodes. Basically, nodes are the points of destructive interference as the waves move past one another back and forth. And there you have zero displacement or very minimal displacement, no movement at all if you're looking at water waves. And antinodes are points of constructive interference where we have maximum displacement. Consider two coherent sources of waves in a ripple tank. These waves vibrate at the same frequency and produce identical waves which form an interference pattern as shown over here. Waves vibrating at the same frequency. This is the interference pattern that you would observe. This is nicely observed with water waves in a ripple tank. Now we have got these dark lines over here, these dark areas here. These are the crests, they represent the crests of the wave. And the lighter areas in between are then the troughs of the wave. And this huge area in between these lines here, these areas, are then areas where the water has been quite disturbed, so they represent constructive interference. We also then have lines almost that look undisturbed. Those are areas of destructive interference. In fact, we refer to these lines, the areas of destructive interference, as nodal lines. So in our diagram here, there is a nodal line, and another nodal line, for example. If we use a wavefront diagram to explain this interference, it would look like this. We have two sources. Remember, these sources are coherent sources, source 1 and source 2. And we need a key to explain this complex looking diagram. Thick lines. The thick lines represent the crests, and the thin lines represent the troughs. So what actually happens here, the little red dots, the line through the red dots represents constructive interference, because you'll notice that at the red dots you either have got a crest meeting a crest or a trough meeting a trough. So those would be areas of constructive interference or paths of constructive interference. The blue dots, if you were to draw a line through them, they represent destructive interference, because at these dots you have a crest meeting a trough. In other words, a thick line meeting a thin line. And if you were to draw lines through all the blue dots, those lines we refer to them as nodal lines. This is the parts where the crests meet the troughs, where we have destructive interference, where we see almost no movement. And if you draw in the red dots, is where we have the maximum disturbance lines. That's where you observe your constructive interference. In other words, the parts where the crests meet the crests or the troughs meet the troughs. There is a possibility of interference at a point, but whether or not there is constructive or destructive interference at a particular point depends on the distance the two waves travel before they meet at that point. If you consider an interference pattern here, we have two waves coming from point A and point B, and we consider a point P somewhere in the interference pattern. The waves traveling from source A will have traveled the path AP, and the distance therefore is the distance from A to P. And the waves traveling from source B would travel the path BP. Path difference is the difference in the distance traveled by the two sets of waves. So in this case it will be BP minus AP, and basically the distance from B to C there is basically the path difference of this particular wave. We will have constructive interference at point P if the difference in the path length is a whole number of wavelengths. In other words, we'll have constructive interference at that point if the path difference is equal to n times lambda. N is basically the number of wavelengths, where n it could be 0, 1, or 2. Also, at point P, we will have destructive interference if one wave travels an odd number of half wavelengths further than the other wave. In other words, we will have destructive interference if at that point the path difference is n lambda divided by 2. That's what we mean by half wavelengths, where n in this case is 1, 3, 5, or 7, etc., etc. Our last concept in this lesson is the concept of shock waves and sonic boom. Now, very often some aircrafts like fighter jets or space shuttles, they actually travel at a speed faster than the speed of sound. And the relationship, or when you divide the speed of the aircraft by the speed of sound, you get what we call the Mach number. For example, an aircraft flying at Mach 2, it's basically flying at twice the speed of sound. Now, in relation, when we look at the relationship between the speed of the aircraft and the speed of sound, we have what we call subsonic speed and supersonic speed. Subsonic speed is when the aircraft speed is less than Mach of 1 or Mach number of 1, and this often happens in the Doppler effect. And in the case of supersonic waves, the aircraft speed is greater than Mach 1, and this happens in what we call shock waves. Basically, this is when the aircraft is moving much faster than the speed of sound. The result is actually what is called the sonic boom, and as the name implies, you hear like a huge sound explosion. We've come to the end of this lesson. Please remember to watch each DVD at least more than once for maximum benefit, and also to do the worksheets that accompany each lesson. For additional challenges on this lesson, you refer to the grade 12 copy of the Study and Master. From page 84 to page 86, you'll find 2 activities that are dealing with 2D and 3D wavefronts.